All right, back again. We are talking now about gas liquid solutions. So this would be a solution with a gas dissolved in a liquid. Most gases have quite weak intermolecular forces, which is why they are gases in the first place, which means many of them are non-polar molecules. And so what happens is dissolving the gas particles also is disfavored entropically because gas likes to be in the gas phase. So by dissolving a gas, you are working against entropy. You are decreasing the entropy of the system, which is unfavorable for making something spontaneous. So usually for gases dissolving in liquids, entropy is against you and enthalpy is against you. So typically gases are not super soluble in liquids. This is especially true the more polar the liquid becomes. So for water, if you look at something like oxygen, its solubility is only around 10 to the minus 3 moles per liter, which is very, very low. And compare that to something like sodium chloride, which has a solubility of 5.4 moles per liter, which is 5,000 times higher than it is for oxygen. And we know that that dissolved oxygen in water is extremely important for aquatic life, for things like fish, because they need to breathe oxygen, not breathe, I guess, but extract oxygen from the water in order for them to survive. Carbon dioxide is an actually quite interesting case because carbon dioxide is much more soluble in water than you might otherwise expect. And that's because carbon dioxide will react with water to form carbonic acid. And the way you can think about this is, the CO2 gas is basically, once it dissolves into the water, because it's turned into carbonic acid, that allows more CO2 to dissolve in the water. However, what this will do if you put a lot of CO2 into water is it'll decrease the pH, makes it more acidic because of the carbonic acid, and that can have negative effects on wildlife. Well, one thing that we do know is that the solubility of a gas in a solvent is directly proportional to the pressure of the gas, the partial pressure of the gas above the solution. And this relationship is known as Henry's law. It's a very simple relationship. The solubility of a gas is equal to the pressure of the gas above the solution multiplied by a constant K, which is called the Henry's law constant. So for example, carbon dioxide may not be all of that soluble in water. However, what we can do is pressurize the CO2, and that will drive more CO2 into solution. So if you double the pressure of CO2, you'll double the amount of CO2 you can dissolve in a given volume of water. So this is actually an interesting example of this. It's a lake in West Africa called Lake Nyos. And what happens with this lake is it's built over sort of a volcanic crater. It's filled up with water, and at the very bottom of the lake there's little fissures that allow carbon dioxide to sort of slowly rise up. Because the pressure at the bottom of the lake is so high, that allows for very, very high concentrations of CO2 to dissolve into the water. And typically because of layering of levels of water in the lake, often by temperature, that leads to extremely high dissolved CO2 concentrations in the bottom of the lake where the pressure is high, much more so than at the top of the lake. In August 21st, 1986, there was something called a limnic eruption, which what happened was there was a mixing of layers. Some of the very high CO2 concentration areas at the bottom of the lake were lifted at the top. I'm not sure if they know exactly why that is, whether maybe there's a landslide and some, solid material came into the bottom of the lake and pushed some of the liquid up, whether it was rain or whether it was some other thing. What happened, though, was that some of the deep down water moved towards the top of the lake, and when it did that, the pressure went down significantly, and the solubility of gas went down significantly, and the CO2 came out of solution. It started to bubble out. That bubbling caused a lot more mixing, and basically it caused the bottom of the lake to be mixed up completely, and it, in a very short period of time, emitted a huge amount of carbon dioxide. Giant CO2 cloud came out of Lake Nyos into the surrounding area. It suffocated and killed 1,746 people, 3,500 livestock as well. It's a grim but interesting example of Henry's law. So what they do now, actually, to prevent that from happening again, is they degas the lake. And you can see this in 2001. Basically what they're doing is they are sucking water from the very bottom of the lake up so that it doesn't sort of build up to those extremely high CO2 concentrations as would happen before. So this is a chart that's showing solubility of different gases at different temperatures, and what you can see is that most salts, most solids, increase in solubility as you increase the temperature of the liquid. You see lines like this for KCl, solubility goes up. Ammonium chloride, potassium nitrate, sodium nitrate, potassium iodide, so on. But for gases, things like HCl, which is a gas at room temperature, so is ammonia, so is SO2. These all go the opposite way. When you increase the temperature, it decreases the pressure. So you can see in the picture right here, what's going on is there's a bottle of champagne. When the top comes off and the pressure on the inside is suddenly dropped, that can cause the gas that's dissolved in the liquid to come out kind of all at once. And you can see it, of course, spraying everywhere. That's much more likely to happen when the bottle is warm than if the bottle is cold, because the solubility of the CO2 or any other gas in the liquid is lesser at higher temperatures. So we're going to use Henry's law here. Basically, Henry's law says the solubility is the kH, which is the Henry's law constant, times the pressure. We're told that the partial pressure inside a can of Pepsi is 4 atmospheres at 25 degrees Celsius. What's the solubility? And we know what the Henry's law constant is at 25 degrees Celsius, conveniently in units of atmospheres, which is great. So this is actually pretty straightforward. We say the solubility is equal to 3.3 times 10 to the minus 2 moles per liter atmosphere. Multiplied by 4 atmospheres, and that just equals all right, so just got something going on here for a second. Bear with me. Okay, so that equals, 0.132 moles per liter. And I guess we really only have one sig fig here, which means we've got to round this to 0.1 mole per liter. And that's our answer. All right, next unit we're going to talk about is colligative properties. And colligative properties are interesting. They are properties that depend only on the number of solute particles dissolved in solution, not on what those particular dissolved particles are. So just that there's solute dissolved in there, doesn't really matter what the solute is. The 4 that we're going to be looking at are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. All of these colligative properties depend on just how much solute there is in solution, not on what the solute is, as we'll see. The Van 't Hoff factor is something that we have to take into consideration. What this does is it accounts for the fact that some particles, when you dissolve them in water, for example, will dissociate and give you more solute particles than there were formula units that you dissolved. So sodium chloride, for example, if you put it in water and it completely dissociates, will break into, so one formula unit will break into 2 particles. 1 Na plus, 1 Cl minus. So if one formula unit gives you 2 particles, we would say I equals 2. Right? So if you had something like calcium nitrate, that would break into 3 particles, which is calcium 2 plus 2 NO3 minus. So we would say that its Van 't Hoff factor I is 3. So we have to use the Van 't Hoff factor when we are using things that dissolve in water that dissociate. So exercise 6 says, what's the Van 't Hoff factor for each of these following solutes? And you just look at what they would dissociate into if you put them in water. Na plus plus OH minus will give you a Van't Hoff factor of 2. Sodium bisulfate would also be 2. Calcium chloride would dissolve into 3. Aluminum tribromide would dissolve into 4. Potassium sulfate, that'd be 2K plus plus SO4 2 minus. It's 3 particles for I. Glucose is an organic molecule. Many organic molecules, probably most organic molecules, don't dissociate in water. That's because there's no ionic bonding. It's all covalent bonds. So this would have a Van't Hoff factor of 1. 1 formula unit gives you 1 particle in solution. So the vapor pressure, if you remember, it's the pressure above a liquid when it's at equilibrium. It depends on the relative strength of the intermolecular forces, how strong the intermolecular forces are holding the molecules together. If they're very strong intermolecular forces, you typically have lower vapor pressures, and the liquid we would say is less volatile. At temperatures, typically higher temperatures, more molecules at high temperatures will have enough kinetic energy to enter the gas phase. So vapor pressures are higher at high temperatures and lower at low temperatures. And of course, we have the Clausius-Clapeyron equation, which describes that more quantitatively. Third one that we're going to introduce right now is the presence of a solute, solid or liquid. If you dissolve something into a liquid, that's going to lower the vapor pressure of that liquid. It's called Raoult's law. The presence of a solute will reduce the vapor pressure of the solvent over the solution. So we got a busy slide here. We have a picture right here of a pure solvent in equilibrium with its vapor. And so the P0, the 0 would be the vapor pressure of the pure solvent. When you have a solution made from that solvent, we would just say that's the vapor pressure under, I guess, non-ideal conditions or conditions where we have some other thing dissolved in there. The way you can think about it is for something that's not at its boiling point and it's evaporating. We said evaporation is a surface phenomenon, that it's molecules that are at the surface that are going to be entering and leaving solution. So if you dissolve something in there, I mean, one way to think about it is that some of the particles that are at the surface are not the solvent particles themselves, but they're in fact the solute particles. So what we could say is that the total pressure of the solvent, the partial pressure of the solvent, is going to be equal to the mole fraction of the solvent multiplied by the vapor pressure of the pure solvent, which is P0. Mole fraction of the solvent is just the moles of the solvent over the total moles of particles in solution, which is the moles of the solvent plus the moles of solute multiplied by the Van't Hoff factor for each one.